of ICFP, a section all about model checking and slicing. And the first paper in this session, a traversal-based algorithm for higher order model checking. And the speaker is Robin Neatherway. Thank you.
Okay, thanks for coming. So today I'm going to be talking about higher order model checking, which is a technique, an automated technique for program verification. We've made a few contributions in our paper, and I've outlined them here for you. First, we've introduced a new model of higher order computation, which are higher order recursion schemes with case, or HORSC. This is a restricted form of higher order computation compared to what you might be used to, such as programming languages like Haskell. And so we were able to give a proof of decidability of the model checking problem against a class of automata by reduction to type inference. And this proof is an extension of some work by Kobayashi. We give a practical algorithm which is inspired by, but doesn't use directly, the game semantic notion of traversals. Traversals were originally used by Ong for the original proof of decidability of plain higher order recursion schemes. Further, we've implemented and given an evaluation of our tool, which incorporates earlier work by Ong and Ramsey. So for this talk, I'm going to be focusing on the model of computation, that is HORSC, and the algorithm that we've given. If you're interested in traversals, please see the paper. So first, we'll look at some preliminaries. What are HORSC? Well, you can think of them as a pure, simply typed, higher order program with constructors, but no destructors. Now, one ramification of this is there's no pattern matching. So you can't use the normal control flow structure that you're used to. But we do offer some form of control flow with a case construct. This operates on nullary constructors of a distinguished type, which we call D. You can think of this as standing for data. Other constructors are built out of type O, which you can think of as standing for output. The HORSCs can be non-deterministic, and therefore they can generate a set of trees or terms, if you like to think of them as terms. Here's an example. This will be our running example throughout the talk. You can see that we have an alphabet, sigma, of constructors. Two of them are of type D. These are the nullary constructors I was talking about, and we can pass these to our case construct. These B1 and B2. We've also got 0, suck, and pred. So we can build trees out of these, such as suck of 0, or pred of 0. We have some non-terminals, or function symbols, S, H, and G, and some rules. These look just like ordinary function definitions that you might be used to. You can see we've used the case construct here in our definition of S. H is the scrutiny term. So what H reduces to will determine which of the two branches we choose. If it reduces to B1, we'll choose the first branch. If it reduces to B2, we'll choose the second branch. H is non-deterministic, so we can see that it can only reduce to B1 or itself. To have an idea of how this program will reduce, I've done the reduction sequence for you here. This is one possible reduction sequence because, of course, it's non-deterministic. Starting from S, we rewrite to the right-hand side case of H, G of suck, and G of pred. Then we reduce H. As it's not a member of the nullary constructors or the finite data domain yet, we have to reduce it. It reduces to B1 using this rule. Now, we can reduce to the first term because this scrutiny term is B1, and we get G of suck. Applying this rule, we then rewrite to suck of 0, and this is a tree generated by this HORSC. Now, if we can use these HORSCs as a model of higher order computation, we'd like to ask some questions about the kinds of trees that they can generate. And we'll do this using the kind of automata. These are deterministic trivial automata. If we consider the simple HORSC here on the top left, we can see the tree that it generates on the top right. It generates all possible even natural numbers, just by adding an extra pair of successors each time it recurses. But maybe we'd like to check that this is actually what it does. So we can give an automaton using this kind of specification. Starting from the initial state Q0, the automaton operates over the alphabetic constructors used in the HORSC. The transition function is given here in the bottom left, and you can see this rule, as it operates on trees. If we're in state Q0 and we see a branch, then we transition to Q0 for both of the children. If we see suck from Q0, we go to Q1. If we see another one, we go back again. And if we see 0 in state Q0, then we accept. If we saw a 0 in state Q1, we'd be stuck and we'd have to reject. We can check whether the tree is accepted by the automaton by a process of annotation that you can see here. Of course, as the tree in general is infinite, this wouldn't terminate. But this gives us an idea. So starting at the root of the tree, just this tree given here, in state Q0, we transition for both the children to state Q0. When we see 0 here, we accept, and we move on to check this right-hand branch. Again, both the children must be in state Q0. When we see suck, we transition to Q1, back to Q0, and again we accept. Now, I hope you can see that we'll be able to continue this annotation process infinitely across the entire tree. Now, as this process wouldn't be guaranteed to terminate, the tree being infinite, we'll have to come up with a cleverer way of doing it. Here's another example of a trivial automaton, and we're going to use this to check a property of our HORSC that I showed you before. It just checks that we always see at least one suck before we see a 0, as zeros are only accepted from state Q1. If we saw one in Q0, we'd be stuck and we'd have to reject. And here's the annotation of the simple tree suck0 that was generated by our original HORSC. So how are we going to answer this question? Are the set of trees generated by our HORSC accepted by a given automaton? Well, we do it using a type system. This is an intersection and union type system, and it's induced by the property automaton and the finite data domain. The finite data domain is our set of nullary constructors that we can use our case construct on. These are not general intersection and union types. They're used only to refine the simple typings that we already had for our original HORSC. And they can be used to describe the input and output behaviour of the HORSC and its function definitions in terms of the property automaton and the finite data domain. For example, given a state Q from the automaton, if you can give a term of base type, that type, Q, that guarantees for us that any tree generated by that term would be accepted from state Q of the automaton. Or equivalently, we could perform the annotation that I showed you previously without ever getting stuck in the transition function. Furthermore, a valid typing for the HORSC as a whole implies that the property is satisfied, and I'll explain what this means in a bit more detail. This type system built on one from Naoki Kobayashi. We use the union types here to help us handle our finite data domain. The form of the intersection and union types that we allow is given here by these three induction rules. So, state Q, any state from the automaton, refines the simple type O. Any finite union of symbols from the finite data domain refine type D, and arrow type we allow intersection on the left. Normally you can have intersection on the right of an arrow. We don't allow that, but it's not a restriction, it's just a technical convenience. Notice that all of the theta i's that appear on the left of an arrow must refine the same simple type, so they must all have the same shape. There are some examples given here of intersection and union types, and the simple types that they refine can be seen on the right. So here we have the example HORSC again, and the property automaton that I gave, and some example types that we might like to give terms. 0, we should be able to assign the type Q1. That's natural because it's accepted from the state Q1. Suck is an order 1 constructor, and we could give it both of these types, Q1 to Q0 and Q1 to Q1. Now you'll notice that if you see a suck in the tree in state Q1, you transition to state Q1. So if we give it a term, or a tree, that's accepted from Q1, then it in turn should be accepted from state Q1. So suck of 0 would be of type Q1. You can see the types here. The argument type will line up. H, we should be able to assign type B1, because it can reduce to B1. And G, this higher order type here, should be able to take arguments of type Q1 to Q0, which is the type we can give to suck, and return a tree accepted from state Q0. And this makes sense because suck of 0 is accepted from state Q0. Here are the intersection type rules. This is the original type system of Kobayashi. Just these 4 rules are sufficient for plain higher order recursion schemes. The var rule is fairly standard, although do note that we may have multiple bindings for variables in our context. The term rule is where the automaton allows us to assign types. And you can see here that if we're in state Q of the automaton and we see a terminal A, or a constructor A, and it requires that its n children be accepted from states Q1 to Qn, then likewise the type that we assign to A requires the same thing, that the arguments that it's applied to are accepted from those states Q1 to Qn. The application rule requires that if T1 has some intersection of types to theta, then for each of those theta i's in the intersection, we must be able to show that T2 has that type. So this intersection is of size n, we'll have n derivations for T2, and only then do we know that T1 and T2 has type theta. The abstraction rule, for each member of the intersection, we can pull that out into the context. So this is how we can have multiple bindings for a single variable. To these, we add just 2 more rules, where we use the union types. We have, for the case rule, if T has some union of base types of representing members of the finite domain, then for each Bi that T could reduce to, as indicated by this type, each of the Ti's, we have to check their type as well, because this term could reduce to them. At the top level, we can assign Bk a union, any union that contains Bk. Now we can prove a nice theorem about this type system, and that is that the set of trees generated by a horse is accepted by the property automaton if and only if we can find a type in the environment where we prove that the start symbol has the type of the initial state, and for all bindings for a non-terminal f, all of the right-hand sides can be type checked with the same type. Just a natural kind of consistency requirement. And we've extended a proof by Kobayashi. This is a witness for the running example. But we can't just pull witnesses out of thin air. How are we going to come up with such a witness? Because there are only a finite number of types, because their shapes refine the simple types that we've been given in the input, we could just guess and try all of the possible witnesses in turn. But this isn't likely to terminate in any reasonable amount of time. So I'm going to quickly show you an algorithm for deriving such a witness. Just got the horse and automaton here, and as the correctness theorem states, the most important thing we need to check is that S has type Q0, or that the terms, trees generated by S are accepted from state Q0. At the moment, our prospective witness is empty, but to close this judgment, we need to use the var rule, so we're going to have to assume that S has type Q0, and that will place a requirement on us to check that the right-hand side is consistent. Notice here that we just have the right-hand side. Next, we'll have to use the case rule. This will require us to assert that H has some type. Now, for the moment, we'll just assume that it's the empty union, and we'll use a type variable, which I've got up here, beta, to represent that. Because this is the empty union for now, we don't have to check either of these. We're hoping for the moment that H will diverge, for example, and not be reduced to any member of the finite domain. For consistency, we have to check the right-hand sides after we've assumed that H is type beta, and we find ourselves with two requirements to show. Let's try the right-hand one to start with. To show that B1 has type beta, we want to use the base rule. If you remember, this requires that B1 be in beta, so we'll add it up here. However, our use of the case rule will no longer be consistent, and so we'll have to jump back like this and add a judgment for G of suck. Now we'll have to use the out rule. Again, we'll hope that suck won't be used. This is analogous to the empty type variable we used for H. Here it's going to be alpha 1. We've assumed that alpha 1 is empty for the moment, and so we don't need to show anything about suck. Again, we add G to our prospective witness, and we have to show the right-hand side. We apply the abs rule and the application rule. Again, alpha 2 is initially empty. Now we need to use the var rule, and this is going to require that alpha 1 is at least alpha 2 to Q0. So we'll add it in our map of type variables. Much as before, this use of the application rule is now inconsistent, and we have to jump back and check that suck has this type alpha 2 to Q0, because that's in the intersection that alpha 1 represents. Looking in the automaton, we see that suck has type Q1 to Q0 using the term rule, and we modify alpha 2 and jump back. 0 has type Q1, so we're done with this particular area of exploration. Notice that we still have an empty, an open environment, an open judgment here that we haven't been able to close. And you'll probably notice that this could go on forever because H can reduce to itself. So we don't know when to terminate. However, if we look at the tree of dependencies of the types, we'll find here that H, this particular right-hand side of H, depends on showing the same typing environment. So we can kind of close the recursive loop here, and we don't need to explore this any further. In general, these types can be arbitrarily complicated though, so the tree will in general be much larger. It's guaranteed that if we can find a point where all the types are consistent in this manner, and there's nothing left to explore, then we have a witness in the sense of the correctness theorem. And so, because the number of types is finite, we're also guaranteed to terminate. To conclude, we've offered this new model of functional computation, PORSC, and they extend higher order recursion schemes with a case construct. And we believe this is a more natural way of expressing abstracted functional programs. We've given an algorithm for solving the model checking problem, and in the paper we've shown a correspondence with traversals used in the original proof of decidability. We've used our implementation to verify a number of safety properties of programs written in Turing powerful functional languages. And that's all for now. Thanks very much.